You need continuous update. Everybody connecting to everybody else to update. Because if you haven't, noticed the latest release of OpenAI, the reasoning version, you're wasting your time. So you need to set up everybody's work is recalibrated continuously with respect to nearly everybody else. That's communication. We come to that. But also, be looking different. Because now everybody is different specialists. There are the scientists, the engineers, the artists. You need all of them. The finance, the bankers, the entrepreneurs, the startups, the IT. In a crowd, you need to be able to spot them, and you do. So I'm talking about the seniority of professionals. And you have to calibrate how you will appear. You don't really mix up with an investor or banker. Nor would you want to mix up with an engineer. So you have to kind of find, and you want to express something different anyway. So and you want to reinvent yourself. And the office starts to look like this. In some offices, this is Google office. And they're also differently organized. The teams continues the transformation, shifting, revolving. They're not separate. You belong to several teams at the same time with a different degree. The fuzzy logic of this kind of blobism comes through. Instead of strictly nesting, you have intersecting and overlapping. You have these kind of spaces where you both overlap and degrees of belonging and fuzziness. So this is the kind of models, and it's dynamic. We move from year to year. This is a project we're doing, for instance, for the Sberbank Technology Center in Moscow. Banks are IT companies now, as well. And that's the kind of world we need to develop. And that's where the prosperity gains are. That's what you have to participate in. And these are the kind of spaces, inter-awareness, inter-visibility. This is the project we've done in Beijing. Now all offices in there. There's co-working spaces. There's also restaurants and bars and offices and retail. And you will see what's going on. Okay. This is my book. I'm not going into detail here of this. I've seen this. Sorry, I'm bit repeating this. Sorry if it's wrong. Okay, so just aside. So as I said, Tectonism has been a while in the going, and it actually the first within parameters, the first glimpses started already in 2000. So it's not my invention. I'm the one who's kind of a synthesizer and productizer and promoter, and Frei Otto became interesting again. I was actually a student in the 80s in Stuttgart, because this is form finding. He was also some early loose algorithms, but this seems to be something kind of separate. Architecture moved somewhere else. It moved modernism, postmodernism, deconstructivism, and so on. Frei Otto was forgotten. But then we rediscovered him. And then it's very fundamental, these form finding processes for Tectonism. You see these shells, they're very adaptive. We have 4 stations in Innsbruck, underground, close to a bridge, on the hill, on top. So it's one principle, but it's parametric variation. Usually say the stations, now if you do a train station, it's repetition. This isn't, it's a set of principles, parametric variation. And they're also shell structures, so they're optimized. And then also, instead of cluttering details, plugging on a drainage pipe or this and that, the drainage is just one of the seams opening up a bit, so you don't clutter the thing. And you have here a kind of correlation between 2 systems. The concrete platform, an undercroft, and the top. They have some different logic, but they correlate, they relate to each other. They're not separate, they have to correlate. We started this early on, 50s, carbon fiber shells, tensile structures. So this is the beginning of Tectonism. And again, we had somebody like Mark Burry, so it's not only us. And Lars Freiberg, so it's been going for a long time. And Mark Burry, who was the architect computationally completing the Sagrada Familia of Gaudi. And even something like Riser, Atlas of Novel Tectonics. So it also shows digital tectonics, novel tectonics. These phrases of tectonics were swinging around in the last 15 years, so that's why I picked up the name Tectonism. It was the desire of parametrism relating to the tectonic. And these are studies which were many years ago at Vienna University. So instead of having a shell like, for instance, Foster has parametric tools. He did the great roof over the British Library. But when you look at it, he uses to smoothen out. So everything we use as homogeneous as possible. Because we love that this is different. Oh, instead of ribs, they close web, gridded, tensile shell. So under this you can imagine many different subsidiary spaces, different zones, but not separated by walls. But you can orient, use that ceiling and space to differentiate an event in different subsidiary spaces. But the concept of tectonics is some kind of heightened artistic, inverted commas, expression of structural logics, fabrication logics, material logics. Is a very old concept in the history of architecture. And I do like that. I want to build on this because we're doing tectonics in a new way. Parametric tectonics, tectonism. And of course, I looked at these. They're wonderful, they're structurally optimized and super high performance structures, but they also at the same time become ornament. And that's what we're talking about. Ornament is actually semiological expression. This kind of styling of and giving identity and character to different spaces. That's a task for architecture too, not only technical. But what we've done, for instance, or you have these kind of bizarre hybrids of Vieux-le-Duc, or somebody like Frank Lloyd Wright. So we have these principles or engineering parts. So we're using structural form finding and optimization as one major part, but also environmental engineering, and then fabrication constraints. How to make things, whether you're casting or whether you are hot wire cutting the mold for casting or milling the mold for casting. This all implies different geometries where you use tensile structures, etc., etc. So what kind of fabrication do you do? And what is interesting for the first to realize, I said it earlier, so some of these walls, they're compression-only walls. Eventually, the horizontal forces have to be taken out by, frames on the outside. But they only could do that traditionally by making perfect symmetry, because this is an equilibrium composition. And even you can actually learn this when you read Palladio, that symmetry in all buildings is a structural necessity at that time, not only in these walls. Because if you build a building and you have asymmetry, put a tower here, you have differential settling of the foundations, and the building will crack up because you can't calculate. So the symmetry was and asymmetric buildings, you have cracks all over the place. They will break up, they fall apart. So some of these are, formalized as an aesthetic structural logic, simply proportion. What is proportion? Proportion is, of course, that you have the height to length of the column, that you have spans, maximum spans, and depth of beam, or etc., etc. So all of the symmetry and proportions of classical architecture are aestheticized structural logics. Now we can do this. You can be any free form, because we need to compose the spaces in complex relations, and it would be really a hindrance for a versatile adaptive design that we have to make everything symmetrical, because the institutions are unsymmetrical. There's no mirroring over of space, it makes no sense. So but now we can do this. What is wonderful, it also calculates each stone optimizing, and you can see how these slender these shells are. These marble shells, they have no bonding. just pure compression. They're pure equilibrium. If you go to this model and you kick out 2 or 3 stones, the whole thing will rain down. And there are also ones which I don't have here, compression and tension. There's a loop. And if you go in and cut this, you can learn from the traditional, but we can do it much more there. Or if you look at waffle slabs, or any concrete, even the laying of reinforcement, all traditional engineering is obsolete and irrational because it's inefficient. You have to follow the forces. If you put columns in the corner, why do you have a waffle grid? Why do you have reinforcement going in straight lines? You're wasting a lot of material. You also can thin out in the center. And then, so this is what we have to do. And isn't that way more beautiful? And doesn't it tell you where the column will be and where the opening will be, so it's more legible and orienting, and you can run this across a shell also. So we have these kind of optimization of stress, primary stress lines, and that's what we should use. And then this is a kind of 3 high pass connected up based on a Candela model, but using this. And then using the stress analysis to layer those areas which have more stress in 2 or 3 or single layer. But isn't it more elegant and beautiful? Wouldn't you cringe if you had to impose a rectilinear grid on this? We have a sensibility for that. So that's tectonism. If you look at this chair, it's super, here we have fabrication, we're doing 3D printing, so we are not totally unconstrained on the whole science. 3D printing, material concrete printing, there's enormous amount of constraints, and I come to this, but it's less constraints than we usually would have. So we can super optimize. So we take a form, a functional form, we then kind of stress, relax, and optimize the shell form. Then we can run structural optimization on that surface for the reticulation. And then there are different ways of translating this. For instance, thinning out versus thickening up, plus degrees of perforation. You could do one or the other. So there's enormous amount of creativity in the translation. So it's not, it's not never automatic, but you can play with it. And then you get something like this. And then you can print that in plastic or in aluminum, and it's the strongest and lightest chair you can ever have. But of course, there's other versions that you can further optimize. You can do something similar to larger structures, but then the fabrication sort of printing is more rationalized. It's straight lines and developable surfaces, but they'll probably resonate. So similarly with these shell, but then the first 2 steps are the same: shell optimization, reticulation optimization, and then there's a fabrication translation into straight line and developable surfaces for the holes. Anyway, for instance, towers. I guess you've all learned that. There might be still in the curriculum. You say, okay, up to a certain height, you only need a framework, then you need to have a core and framework, then you need to start putting outriggers, and at a certain height you flip into exoskeleton, meaning you use the outer surface like a tube. Now, I'm saying there is a fundamental flaw here, which is the thinking in pure systems. You can take this diagram upside down, and it tells you already how absurd it is. Because the forces accumulate exponentially, wind forces and wave forces. And that's one thing. Of course, you do that by making the columns here much thicker and thinner than ever. But also the system separation is wrong. I'm proposing where you start with the tube and move into the outrigger and then into framing. And you can also also phase change systems. So that's what these kind of things we've been doing. And you cannot flip it on top, around. So, and these are still crystal, they're not kind of optimized, it's still symmetry, but it's a step for these kind of projects. And this way you can also then differentiate the product. 3 flats, 2 flats, 1 flat per floor, you can open up the column and get much more filigrane light on top. And you get much more, let's say, framing action in the bottom. The other thing is when you do exoskeletons, you can release enormous amount of internal visual connection and freedom. So the tower, you should actually be like a vertical street instead of everything separate, floor by floor. And even on the floor, through a central core, separating the rooms. Everything is segregated. You're in a building with 10,000 people and you all disappear in the corridor and never see each other. When you put the exoskeleton and run panoramic elevators, you can see what's going on. You're flying over the restaurant, the bar, the cafe, the conferencing, etc. The lobby, you keep seeing things, you look back into the urban spaces, etc., etc. This is the kind of thing we're going to do. Anyway, so many examples of this. So you're doing this kind of shell optimization, we have reticulation, and this is where you can start have an artistic inverted commas. You have repertoire, you can translate this in extruded ribs, more, less, pleats. You can go into openings as well, and you can have a whole variety of characterful differentiation, and you can therefore give each space a different character, degree, and it becomes, structure becomes ornament, like an auto-vision architecture. And ornament is characterization, semiology, information communication. This way we combine tensile structures and shell structures, something Toronto also never did. So we started to say, okay, instead of having a tensile structure run off pylons, we have the tensile structure running off vaults. This was our winning entry to the Tokyo Olympics. Or we have done something like this in large structures like the airport in Beijing. More recent projects. Grid shells, and again, you don't have to make them even grids, and this is, it's not fully optimized. For our tour, it's interesting. So here, this kind of path network optimization, but circuitry path, you can make the analogy to load path. So these become, you materially compute irregular load path networks onto irregular support points, for instance. So I did a project I was teaching at Harvard, and did this kind of project for Google Campus, and one of the themes was using this and all the variation you can generate and translating into different materials, timber versions, the smaller ones, steel versions, the larger ones. All sorts of shells in this way, double height, triple height, etc. Another team was doing grid shells, active bending. Another team was doing catenaries and catenaries, inverted, and then differentiating out. So that's tectonism differentiating out. My conclusion at the end was this: each of these is integral and beautiful and differentiated, but for a huge complex like Google Campus, where you have 25, 50,000 people and hundreds of various types of spaces and entrances, this is still too monotonous. But with tectonism, you can have all 3 and more systems coming in and differentiating out and layering. So I'm not happy with these. Like, up to a certain point, bring many systems and variety together. That would be the ideal thing. And as Google Campus, as you can see, was interesting. We pitched heavily for Google and their page and so on. And they just didn't understand what they're doing, because they said, look, we want somebody who's delivering a zero, net zero. Okay. waste your whole company, 50,000 people waste their time because they're sitting in a net zero bunker.